This video is about the cause of the seasons and the two ways of measuring a day: the sidereal day, which uses the stars, and the solar day, which uses the sun. In the lecture outline, the first set of vocabulary terms is about measuring a day, and the second set of terms is about the actual non-uniform motion of the sun on our sky. The seasonal temperature depends on the amount of heat received from the sun in a given time. To hold the temperature constant, there must be a balance between the amount of heat gained and the amount of heat radiated to space. If more heat is received than is lost, your location gets warmer. If more heat is lost than is gained, your location gets cooler. What causes the amount of energy reaching a given location during the day to change throughout the year? Well, first of all, the amount of energy produced by the sun does not change throughout the year. It is constant. There is a very slight change in the energy output over an average 11-year cycle, but it has nothing to do with the Earth nor with the months-long seasonal temperature changes we experience every year. The seasonal temperature changes are due to angles. The Earth's rotation axis is tipped by 23.5 degrees with respect to its orbit around the sun. Therefore, during the spring and summer, our part of the Earth is angled toward the sun, and during the fall and winter, our part of the Earth is angled away from the sun. To see how the angle can make a difference, let's use an analogy of someone squirting a steady stream of water at you. If you hold your hand face on into the stream of water, you'll block more of the water than if you hold your hand more edge on. The sun's energy output is constant, but the angle of the sun's energy hitting our part of the Earth and the length of time the sun is above our horizon determines the seasons.
During the fall and winter, we're tipped away from the sun, so the sun's energy hits our part of the Earth at a more glancing or shallow angle. The sun's energy is more spread out, so there's less heating power. Also, during the fall and winter, the sun is above the horizon for less time, so there's less heating time. During the spring and summer, we're tipped toward the sun, so the sun's energy hits our part of the Earth at a more direct or steep angle. The sun's energy is more concentrated, so there's more heating power. Also, during the spring and summer, the sun is above the horizon for more time, so there's more heating time. What is wrong with the popular model that says that the distance our part of the Earth is from the sun causes the seasons? Here are three things. Number one, the distance model predicts that the north and south hemispheres should experience the same seasons at the same time. In reality, they do not. Number two, the distance change would cause such a tiny change in the amount of energy we receive from the sun that the temperature change would be less than 1 degree between winter and summer. In reality, the temperature difference is much larger. I run through the calculation in the textbook, so I'll refer you back to that instead of going through the math here. Number three, the distance model predicts that the northern hemisphere should be hottest at the beginning of January, when the Earth is closest to the sun in its elliptical orbit. Even when you take into account the tipping away, our part of the Earth is closest to the sun in early January. In reality, January is the coldest time of our winter. But won't the elliptical orbit of the Earth have any effect? It turns out that the land and water will dampen or reduce any effect of the distance. The next couple of pictures compare the amount of land in the northern hemisphere with the southern hemisphere. The northern hemisphere has a lot more land than the southern hemisphere. At the Earth's perihelion, closest distance to the sun, in January, there is a lot of land near the sun in the northern hemisphere, so it doesn't get too cold. Land heats up quicker than water, and land cools off quicker than water. The northern hemisphere, therefore, doesn't get too hot in the summer, nor too cold in the winter. Contrast that with the southern hemisphere, where all that water means it takes longer to heat up during the perihelion and longer to cool off at the Earth's aphelion, farthest distance to the sun. Again, the southern hemisphere doesn't get too hot in the summer nor too cold in the winter. Distance to the sun is not the reason for the seasons. Instead, the seasons are caused by the changing angle of sunlight on our part of the Earth and the amount of time the sun is above our horizon. Now for how we measure our days. The sidereal day measures the true rotation period of the Earth, the time for a full 360-degree spin of the Earth on its axis. The solar day measures the time between successive noon passages of the sun across the meridian, which turns out to be the same for about a 361-degree spin of the Earth, not 360 degrees. Let's figure out where this extra degree of spin comes from. The sun moves 360 degrees divided by 365.25 days equals about 1 degree per day on average eastward among the stars through the zodiac constellations. Of course, the sun's apparent motion is actually due to the Earth moving, or revolving, about 1 degree per day on average in its orbit around the sun. The Earth rotates, or spins, 360 degrees divided by 23.934 hours equals about 15 degrees per hour, or 1 degree every 4 minutes on its axis. That's also 1/4 degree per minute. The last picture shows why the solar day is longer than the sidereal day. It's because the Earth is orbiting the sun in the same counterclockwise direction as seen from above the North Pole, as the Earth spins counterclockwise on its axis. Therefore, the Earth has to spin more than 360 degrees to get a point on the Earth lined back up with the sun for a solar day. If the Earth did not move around the sun, then the solar day would be equal to the sidereal day. Our bodies care about what the sun does on our sky, so our clocks are based on the solar day, not the sidereal day. That means that stars will cross the meridian about 4 minutes earlier than they did the previous night. It also means that a star or constellation will rise 4 minutes earlier on the next night, and 4 minutes per day times 30 days per month equals 120 minutes earlier, 2 hours earlier after 1 month. The last slide of the lecture describes something called the equation of time, which explains why some actual solar days are slightly longer than other solar days. Where remember that a solar day is the time between successive noon passages of the sun across the meridian. Next slide. Our rock-steady clocks use a fictional mean or average sun moving uniformly eastward along the celestial equator. The difference between this mean sun and the actual sun, which goes up above and down below the celestial equator throughout the year, is called the equation of time. There are 2 reasons why the sun's actual drift among the stars is not uniform. Because the solar day is the time between successive noon passages of the sun across the meridian, when the eastward part of the sun's motion is faster, it takes a bit longer for our part of the Earth to point back at the sun, for the sun to cross the meridian from the previous day. The Earth has to spin a bit more to get lined back up with the sun. The actual real sun moves along the ecliptic, which is tipped by 23.5 degrees with respect to the celestial equator. At the equinox, part of the sun's motion is eastward and part is north-south. At the solstices, all of the sun's motion is eastward. The total motion is the combination of the eastward and the north-south, and that total motion stays fairly constant. So if part of the total is taken up with the north-south component, then there's less available for the eastward part. In that previous sentence, I said that the total motion stays fairly constant, not perfectly constant. The second reason why the sun's drift among the stars is not uniform is that the Earth moves faster in its orbit when it is closer to the sun, near January, and slower when it is farther from the sun, near July. The total motion does change a little. The pictures I have here are exaggerated, so you can easily see what's going on. At aphelion in July, the Earth moves slower, so the Sun does not drift as fast among the stars, and therefore the angle between the sidereal day and solar day is smallest. The solar day will be less than 24 hours. At perihelion in January, the Earth moves faster, so the Sun drifts faster among the stars, and therefore the angle between sidereal day and solar day is largest. The solar day will be more than 24 hours. These two processes are not aligned with each other, so the equation of time plot is this curvy thing shown here. Sometimes the real, actual sun is fast, and sometimes it is slow. The equation of time is also why, even though the longest amount of daylight time will be on the summer solstice, the latest sunset time will not be on the summer solstice, but will be several days later, after the solstice. And the earliest sunrise time will be several days before the solstice.